using the central limit theorem with the rectangular distribution. A quick summary of the rectangular distribution. We have the probability density function, a formula for the mean, variance and standard deviation. In the context here, we're measuring the weight of a 1000 gram bag of sugar. The random variable x is the difference between the recorded measurement and the exact mass of a bag of sugar. So the exact mass, it should be 1000, but it's not going to be 1000. There will be slight differences. Some will weigh more than 1000, some bags will weigh slightly less. But the recorded measurements are not giving the exact mass of the bag of sugar. Here, there's some discrepancy in the actual measurements, and the recorded measurements are within a half a gram from the exact mass of the bag of sugar. So we could say that the measuring scales are not all that accurate. So first part, state the probability density function of x, which is this. Here's the rectangular distribution from minus a half to plus a half here. The width is 1, so the height has to be 1 to have an area of 1 in here. That's why this value here is 1. To find the standard deviation, so just referring to the formula for the standard deviation, will give us 0.289. A bag is chosen at random, and the scales are showing its weight to be 1002 grams. We know the scales are not all that accurate, so the actual mass could be up to a half a gram less than this measurement, or up to a half a gram more than this measurement. So 1002 goes in the center, add a half, subtract a half. And we want to work out the probability of less than 1001.7. So we need the width and the height. We multiply them to get the probability, 0.2. We're working out the mean mass, x bar, that its probability is greater than 1001.95 grams. So it's the x bar value we're working with. It's a sample of 40. There's no mention of the normal distribution here, but we have a large random sample. So the conditions of the central limit theorem, the CLT, are met. So the population distribution is unknown. There's no mention of the normal distribution anywhere. The sample size is large, so it's at least 30. So the sample mean is approximately normally distributed. This is what we're trying to work out. So we're going to use this formula from the normal distribution and sample means to standardize and calculate this probability. Okay, so this is color-coded. The mean mass of the sample is in green. We want greater than 101.95. Standardizing gives a z value of minus 1.09. We want greater than minus 1.09, and the probability tables for the normal distribution give us this. So even though we started off by looking at the rectangular distribution, because the sample size was large and we're looking at sample means, we can use the central limit theorem and the normal distribution to calculate probability.